go. So polar coordinates, what they are is just another way to plot points. So if you were asked to plot the point 3, 4 as an XY ordered pair, what you would do is go 3 units to the right along the x-axis and 4 units up along the y-axis, and there's the point. That's stuff you've done many, many times in the past for lots and lots of various reasons. What your topic is for this week in 172 is polar coordinates. One of your topics is this. And polar coordinates just describes another way to plot points. The ordered pairs is still going to be an ordered pair, but it's an R value paired with a theta value. What we do is the R value is called the radial coordinate. The theta value is called the angular coordinate. And the plotting system, it's not labeled as an x-axis and a y-axis, it's actually a series of circles. And so if we wanted to plot the point 2 with pi over 4, what we would do is rotate to the angle pi over 4. We need to identify where that angle is. I'm just going to draw that angle here in blue. What I've just drawn in blue is not actually part of the graph. It's just kind of an orient. It's supposed to help orient us to the angle. But remember, pi over 4 is 45 degrees into quadrant 1. And what we do is travel along that angle 2 rings from the center, from the origin. So the point in polar coordinates, the point 2 with pi over 4 is at the green point that I've just plotted there. And that's just kind of an overview of polar coordinates. That our point isn't necessarily to talk about those, but what we can talk about, we'll plot a couple of those, and we will practice making conversions from polar coordinates to rectangular coordinates and vice versa. Stuff you've talked about in 172 in the past couple of weeks relates to making those conversions, so we'll revisit those ideas in just a couple of minutes here. But questions about plotting the point 3, 4 or plotting the point in polar coordinates 2 with pi over 4, at least how we just did it. Okay, so what I'm going to do is actually, now that we've talked about kind of an introduction to rectangular coordinates and polar coordinates, we're going to go back to rectangular for a second for a couple of examples. You've looked at rectangular coordinates. Chances are pretty good that those are the only types of coordinates you've seen. At least the majority of the coordinates you've worked with in your mathematical journeys has been rectangular coordinates so far. That's going to change this week, of course. So let's say we wanted to plot the point 1, 5. What we would do is go 1 unit to the right and 5 units up. So there's the point. What if, instead of having the point 1, 5 in rectangular coordinates, how could we express the same point in polar coordinates? Let's think about it for a second. What we need to figure out is the angle we should rotate to, right? So starting from the x-axis, what angle should we rotate to get to that point? In addition to that, how far should we travel from the origin? We can actually determine both of those things by creating a right triangle. Right? We can figure out this angle, and we can figure out this distance by using Pythagorean theorem and trig functions. We know that the distance along the bottom side of the triangle is 1, and the distance along the right side of the triangle is 5. That comes from the ordered pair. And so if we need to figure out x using Pythagorean theorem, x is the square root of, actually, I'm going to not name that x. Sorry, we actually already have an x. We have 1 is technically our x value. I'm going to label this as r. I didn't want to do that originally because r is still kind of new, but I'm going to label it as r because that's actually what it is. But we can figure out r by using Pythagorean theorem. It's the square root of 1 squared plus 5 squared, which is the square root of 26. So if we're trying to write the ordered pair 1, 5 from an xy ordered pair, we want to convert it into an r theta ordered pair. Pythagorean theorem tells us that r is the square root of 26. To figure out theta, we can use inverse tangent of 5 over 1. So inverse tangent of 5 over 1 gives us back approximately 1.37 radians. So our ordered pair is the square root of 26 with 1.37 radians. I am turning my phone volume off. And so, I mentioned at the beginning, there's not, we can spend a fair bit of time talking about polar coordinates and making conversions from polar to rectangular. And we will. We have less opportunities to talk about polar graphs. That's your second topic for the week. But the point is that to convert or to make any sort of connections between rectangular coordinates and polar coordinates, we're going to use right triangles. Okay, sorry, I thought I turned the volume off. We're going to use Pythagorean theorem with a right triangle, and we're going to use inverse trig functions to get the angle. So let's try another one. So 2, 4. That point in rectangular coordinates, that is a point in rectangular coordinates. We can plot it by going 2 units to the right and 4 units up. So there it is. If instead we wanted to write that same point in polar coordinates, we need to figure out the r value and the theta value, which can be done by creating a right triangle, figuring out theta, and figuring out r. R is the square root of x squared plus y squared. This is the square root of 20, which simplifies to 2 times the square root of 5. Theta is inverse tangent of y over x. In radians, we need to make sure we're in radian mode for these. Inverse tangent of 4 over 2 is 1.11 radians. Questions about anything we've said so far? Okay, so let's spend some time now. Let's look at a couple of other pairs of polar coordinates. Let's do 6 with pi over 3. If we want to plot the point 6 with pi over 3, let me change the 6 to a 4. I thought I would, sorry. I have the polar graph I just put in here only goes up to 5, so I don't want to have to travel out to 6. But if we want to plot the point 4 with pi over 3, what we'll do first is identify where pi over 3 is on this polar plane. And you'll see the same. This is actually, I took a screenshot of a picture in the lab manual to use here. This plane actually came out of the lab manual. But how these angles are labeled, just notice that there's a lot more angles identified in here than you are actually maybe accustomed to on the unit circle. Each of the angles identified on the polar plane count up by pi over 12 radians. So this first angle in quadrant 1 is pi over 12 radians. And then the next one is pi over 6 radians. And then the next one is pi over 3. Sorry, I take that back. Pi over 4. 1, 2, 3. And then the next one is pi over 3. And then the next one is 5 pi over 12. So those are the ones, those are the 6 angles inside of quadrant 1. And so if we want to plot the point 4 with pi over 3, we'll go to the pi over 3 angle, identify that, and then travel from the origin, travel 4 rings, or 4 circles out from the center. So same thing we did. This one's the same, of course, as the earlier one we did. But let's say we're interested, since we're starting in polar coordinates here, let's say we're interested in writing this same point in rectangular coordinates. So we're starting with an r value and a theta, and we need to figure out, or we would like to figure out, an x value and a y value. Well, what if we do the same thing here? What if we take this same point and turn it into a right triangle? We know that the length of the hypotenuse here is 4. We know that the angle on the inside here, I'm going to draw it. We know that that angle is pi over 3 radians. What we would like to figure out is the x value and the y value. We can figure both of those out by using right triangle trig, SOHCAHTOA. We know that cosine of that angle, pi over 3, is equal to its adjacent side divided by the hypotenuse. Right? Cosine is a over h. What that tells us, though, is that x is equal to 4 cosine pi over 3. About the triangle, we also know that sine of the angle is equal to the opposite side over the hypotenuse, which tells us that y is equal to 4 times sine at pi over 3. Four cosine at pi over 3 is 1/2. 4 times sine at pi, sorry, that's not true. It's 4 times 1/2, which is 2. 4 times the sine at pi over 3 is 2 times the square root of 3. So those are the coordinates for this same point expressed using rectangular coordinates, meaning x and y. But everything about these conversions comes from Pythagorean theorem or right triangle trig, which are topics going way back to the earliest time anyway, way back to week 1. Questions about anything we did for plotting that one or how we made the conversion from r and theta to x and y? Okay, let's do another one of those. Can be too big. Let's say we've got the point 5 with 7 pi over 6. So give you just a second to plot that one have a shot at it if you want to do that. We'll look at it together in a second. But after we plot it, we're also going to figure out its corresponding point. We're going to convert it from polar coordinates to rectangular coordinates. So we'll figure out x and y. So those will be the three things we'll do: plot the point and then convert it. So 5 with 7 pi over 6. 7 pi over 6 is the second angle in quadrant 3. And what we should do is travel along that angle and go out 5 rings from the origin, which puts us there. If we need to convert it into rectangular coordinates, what we'll do is make a right triangle. What we can do, there's other things you could do. One of our options is to make a right triangle. We know the length of the hypotenuse is 7, and we know the angle in here. Since we're looking at the acute angle there, we're not gonna necessarily use 7 pi over 6, but the angle in there would actually just be pi over 6, right? We're actually using just the reference angle. So if we want to figure out the x value and the y value, we can use SOHCAHTOA with that red triangle. Let's see, I'm going to erase this for a second. So what we could write, though, is that sine of pi over 6 equals the opposite side over the hypotenuse, which tells us that y is equal to 5 sine pi over 6. If we use cosine of pi over 6 is equal to x over 5, which means x is equal to 5 cosine pi over 6. Going back up to sine of pi over 6 is a half, so y is equal to 5 halves. Cosine of pi over 6 is the square root of 3 over 2, so x is equal to 5 times the square root of 3 over 2. But just notice where the point actually appears, which quadrant the point is located in. The point is in quadrant 3. And so when we're stating the ordered pair, the x value with the y value, inside of quadrant 3, both values need to be negative. We need to make sure to include negative signs with both of them. Questions about anything there? Okay, so that's polar coordinates. That's the prereq stuff related to what you'll see this week. Again, Pythagorean theorem and SOHCAHTOA. That's where everything's coming from. Plotting them, we plotted a few. That's not quite a prereq skill, but we kind of needed to plot them just so we could talk about the SOHCAHTOA and Pythagorean theorem stuff they're related to. All right. So your second topic for the week is polar graphs. So you'll be given a polar equation and asked to create a graph. And anytime you need to create a graph, if you were here for our way back in I think like week 3, if you were here for the boot camp, then that was probably the last time we created graphs. But anytime you need to create the graph of something, you can always use a table of values. So here's a function, f of x equals 2x plus 1. In order to create a table of values, what we can do is pick some x values, plug in those numbers to the function to get the corresponding y values, and then we'll have a series of ordered pairs we can plot. So if we plug in -2 back there, we get -4 plus 1, which is -3. We plug in -1, we get -2 plus 1, which is -1. And then 0 plus 1 is 1. 2 plus 1 is 3. And 4 plus 1, that's 5. So we've got those 5 ordered pairs that we can plot to get the graph. -2, -3, -1, -1, 0, 1, 1, 3, and 2, 5. And so when you're working with the polar graphs this week, the graphs of polar equations, you can use the exact same approach. And we'll actually look at one of those in a second. We're going to do one more. We'll create one more graph of a rectangular equation first. But when you get to the polar equations this week, you can do the exact same thing that we're doing here. There's other options you have as well. So if you as you're going through for the week, when if other ways to create these graphs, the polar graphs is shared, and you like that better, of course, that's totally fine. But creating a table of values is an option you have too. So let's say we need to create the graph of x, g of x equals x squared minus 4. We'll literally do the same thing, which is what's kind of cool about using this approach. It's always the same. You always pick some x values, plug them in to get the y values, and then you have the graph. If we plug in -2, we get 4 minus 4, which is 0. 1 minus 4 is -3. 0 minus 4 is -4. 1 minus 4 is again -3. And then 4 minus 4 is again 0. So, whoops, sorry. So what we've got are our 5 ordered pairs, -2, 0, -1, -3, 0, -4, 1, -3, and then 2, 0. Whoops. Again, once we have the points, we plot them and connect the dots to get the graphs. Questions about that one? Okay, so thinking back to 171, in addition to creating a graph from an equation, another task you had back then was you could have been given a graph and asked to come up with its equation. That's a thing you'll be asked to do, potentially be asked to do for this week in 172 as well. So what I'm going to do is put a graph in the chat just so we can all look at it. And we're going to find the equation of that function. So I'll just copy it down here onto the screen. So what we've got for this function is x-intercepts at 2, 0, and 6, 0, and a vertex at 4, -4. So one of the options, or one of the ways you could write the equation of a function, thinking back to 171, is by identifying its x-intercepts. We have x-intercepts here at x equals 2 and x equals 6. What we did back then in 171 was to take these intercepts and turn them into factors that would have produced those intercepts. And so if we want to turn x equals 2, we want to write it into a factor that would give us that x-intercept, what we need to do is move the 2 back on the left side with the x by subtracting it. So that would give us a factor of x minus 2. We want to turn x equals 6 into a factor, same thing, we need to move the 6 back on the left side with the x by subtracting it to get the factor x minus 6. And so for the function in factored form, we can leave it exactly like this. If you want to write it in standard form, that's fine as well. We would get x squared, but we could FOIL to get x squared minus 8x plus 12. But either of those would be perfectly fine. Questions for me about that one? Okay. So I put one more in the chat. Let's work on that one together too. That one has an x-intercept at -3. Another one at 2. And a y-intercept way down here at -9. So if we want to write the equation of this function, what we can do, same idea, same practice, is identify the x-intercepts. We have an x-intercept at -3 and another one at 2. Like we did above, we should turn these into factors by moving the numbers back on the left side with x. For the 3, we should add it. For the 2, we'll subtract it. But there's something unique or different maybe about the x-intercept at -3. How the function behaves at that x-intercept is different than how the function behaves at the x-intercept to the right. The function turns around and bounces off of the x-axis at the intercept to the left. What that indicates is its multiplicity. The multiplicity of that x-intercept is 2. What that meant way back in 171 was that we should put an exponent of 2 with that factor. The multiplicity for the x-intercept at 2 is 1, since the function passes straight through at that spot. That means we should put an exponent of 1, which since the exponent is 1, technically we don't have to put it at all. So the function we get from here is x plus 3 squared times x minus 2. Typically, we would leave the function like this. We wouldn't necessarily FOIL and then FOIL the x plus 3 squared and then FOIL again with the x minus 2. That's a little much. But questions about that one? So What we'll do next to kind of make a connection, at least from the table of values to what we'll be doing this week, is let's say we need to create the graph of this polar equation. R equals 3 plus 3 sine theta. What we can do, like I said, like we practiced, like I said a few minutes ago, is to create a table of values. The values we'll start with, the theta values we'll pick are 0, pi over 2, pi, 3 pi over 2, and 2 pi. As with any table of values you're using, you can always pick more points if you want to pick more. These are perfectly fine to start with. If for some reason you finish up with these and you're still not certain of how the graph looks, or you just feel like you want more points, you can always pick more. But these are always good ones to start with. But how this works, it works the exact same way as before. We'll plug in 0 and calculate the corresponding R value. So 3 plus 3 sine 0 is 3. 3 plus 3 times the sine at pi over 2, that's 6. 3 plus 3 times the sine at pi, that's 3 again. 3 plus 3 times sine at 3 pi over 2, that's 0. And then at 2 pi, we're back at the same spot we were at with 0. So what we've got, though, the outcome of this is exactly the same as with the earlier points. We now have a series of values, a series of polar points we can plot to generate the graph. 0 with 3. Pi over 2 with 6. That one's out here. Pi with 3. 3 pi over 2 at 0, and then 2 pi, we're back there at 3. So this looks maybe kind of funny. As was the case when you were creating graphs in 171, we do need a little bit of an idea or of an understanding of how these graphs actually look, how they actually work. And there's a fair number of different types of graphs you're going to see this week, so I'm not going to quite jump into all of that. But this graph is called a cardioid because its shape looks kind of like a heart. And I'm going to try my best to create a good graph. Kind of hard on the iPad, but the shape looks kind of like a heart. That's where its name comes from. But that is ultimately that's what you're working towards for the week. You'll be using the polar coordinates in order to create the graphs of these polar equations. So of course you have to spend some time. We have to spend some time talking about the polar coordinates so that you can actually put them to work once you get here for the graphs. But questions about that one?